Hello and welcome to this podcast on concept generation and selection for ME450. Our goals here are threefold. First, we will go over the relationship between the design process we're using in the class and the goals of the design reviews. Then we will get into the primary tasks that you are to accomplish between Design Review 1 and Design Review 2. That is concept generation and concept selection. The two basic topics under concept generation that we'll talk about are functional decomposition and brainstorming. The goal is simply to create as many concepts as you can that might satisfy the objectives and specifications that you laid out in Design Review 1. Then, having generated many concepts, you will need to demonstrate a rational down selection, a logical way to demonstrate that the original goals of the project that might have been expressed as weights in something like a QFD table between different attributes and characteristics of your design, that you've somehow down selected keeping those weights and preferences in mind. And that's the process of concept selection. It's a documentation process essentially, and you might use some screening methods to get rid of the bad concepts quickly, and then use a concept scoring table for those concepts that you might be more serious about. So we've been spending quite a bit of time talking about the design process, and the reason we're doing this is because whenever you're faced with a complex engineering challenge, you can think of it as a mountain, and we've talked about that many times already. The idea of a design process is this is a general map, a way of approaching the mountain that generally works, and we've talked about it in the context of this football-shaped design process, beginning way over here on the left at the beginning of ME450, when you just had one paragraph description of what your sponsor may want. You went through this process of benchmarking, of gaining as much information as possible about your project, defining the problem really, and developing a set of engineering specifications. That was the goal of Design Review 1, and now having been through Design Review 1, presumably, you know what your specifications are, and it's time to generate as many concepts as you can. We call that the divergence phase. Again, having generated many concepts, you want to evaluate them, but you don't want to go through a detailed analysis, especially if you've got a lot of concepts that may not be moving forward with. So we call that the transition phase, where you might be doing some rough prototypes, some rough experimentation, some mock-ups, doing some basic analyses, maybe designed for manufacturability or what have you, and then you can rule out some of those concepts. And as you do those analyses, you're going to learn more about your process and your project, and you will go likely and develop more concepts. All right, and at some point at Design Review 2, in fact, you will have your alpha design. That's your first best guess as to what your design is going to be. Being forced to down select through this transition process makes you think about issues you may not have otherwise thought of until it was too late. The fact at Design Review 2 that you've already got a design allows you then to look at it critically, to get feedback from your section instructor and your sponsors, and then in the process of going toward Design Review 3, you may be looking with fresh eyes again on that alpha design, and you could go all the way back to the divergence phase, develop some new concepts that again you'll evaluate, but you'll move through that process quickly, and by Design Review 3 then you'll be at a final design, and that's what you move forward with in the prototyping phase, which takes you to the Design Expo. So up until now in Design Review 1 you've been figuring out what to do, and now that we're moving towards Design Review 2 you're trying to figure out how to do it. Right? So that's this process here of generating as many concepts as you can, evaluating those concepts, and using the knowledge you gain along the way to iterate and hopefully come up with the best alpha design possible by Design Review 2. So as you can see, it's a little bit of a messy process. We're at Design Review 1 now. We're going to generate as many concepts without evaluating them initially. But then we're going to do some rough evaluation. We call that the transition phase, and that's a down selection process. But as you evaluate, as you analyze, as you experiment, as you mock up, then you generate more concepts. So you can see it's this messy process that's really leading to your alpha design. And that's going to involve concept generation, it's going to involve concept screening, feasibility assessment, technology assessment, go, no go. This process of scoring for the concepts that you're more serious about. As you can see, you're only really doing that for a handful of concepts. And then you're at your alpha design. And the whole point is you're going to break that down again and possibly even start over in an iterative kind of a way. That, after you've sort of committed with the best first design, the alpha design, that you can come up with, then you're going to get some feedback, and hopefully it's going to be critical, and that's what's going to move you forward. Now maybe coming up with a whole new suite of ideas, and then rapidly moving through this process again to your final design, which will be in Design Review 3. Okay, so the idea of iterating this outer loop is quite important, and that's really that process between Design Review 2 and Design Review 3, where we're figuring out how best to do it. But that is not the topic of this podcast right now. We're in the second design review phase, where we're coming up with our first iterations and aiming for our alpha design. Again, the more iterations leading to a final design, that's really Design Review 3, and then prototyping will be in the last month of the class, getting you toward the expo, where you can demonstrate that your novel concepts, your novel design is really solving those initial specifications that you set out to achieve early in the semester. So, moving into Design Review 2 phase now, we're talking about concept generation. Diversity is the name of the game. You're trying to generate as many concepts as you can. If you think back to the IDEO video, that was a Nightline video that we watched early in the semester, you remember how they did this. They were not evaluating or judging each other. They had that bell. If there was any judgment at all, they shut down the judgment so as to promote free thinking that would allow as many concepts to be generated as possible. Now, generating concepts without documenting them is not a good idea, so you want to sort of freehand sketch. You certainly don't want to be using CAD at this point. That just slows down the process and might limit your ability to generate concepts. So you're generating documentation, but you're doing this as quickly as you can. And as you do that, if you remember in the IDEO video again, when they were designing that shopping cart, they realized that there was some things that they did not recognize right away. So for instance, they forgot to take the store owner's view into consideration, and theft was a big issue for the store owners and cost. And so they raised issues that required better specification, and that's part of the concept generation process too. You can express concepts in many ways: sketches, 3D models, mock-ups, text descriptions. If you have an idea, particularly if the product is intended for an end user, it makes sense to storyboard the interaction between your concept and the user. So you might say that your typical user, what is his or her name, and how do they interact with this particular product or concept. And writing that out might in turn establish weaknesses and strengths that could lead to new concepts. And one very powerful tool is to combine attributes of concepts. If you've got a lot of concepts, you can evaluate them for where they're strong and where they're weak with respect to their subfunctions. And we'll talk about functional decomposition. And if you use functional decomposition to break down your project and to look at many different methods of achieving subfunctions, you may be able to combine subfunctions into an idea you wouldn't have thought of otherwise through the combination of attributes. Okay, so these are many ways we can express concepts. At Design Review 2, we're going to require that you come up with either a physical mock-up or a virtual mock-up or an experiment, and often it's better as an experiment, that demonstrates really that the alpha design, the kernel of the concept, is actually feasible. Of course, mock-ups, experiments, virtual prototypes, these are great ways to express concepts and to communicate them with your classmates, your section instructor, and your sponsor. How many concepts? This should be dozens. In fact, maybe the number should be closer to 200 than to 20. The fact of the matter is that the more concepts you generate, the more material you have to generate breakthroughs, next generation designs that delight your sponsor and your section instructor. So if you're locking on to 2 concepts, 3 concepts, and you can't get beyond that, there's something broken in the design process. That's a red flag. Why so many concepts? The way I like to think of it is, if you've got a forest and you're looking for a pot of gold in that forest, and you just get on the first trail and start walking, you put your iPod phones in your ears and you just sort of blindly go through the motions walking down the trail. You may get to the end, you might get lost, who knows what's going to happen. But the fact of finding a particular pot of gold somewhere randomly placed in the forest is very unlikely. So you can't just lock onto that first trail. You're likely to prove unsuccessful, but if you've got a lot of concepts, again, you've got a lot of matter that you can combine to create a truly successful concept. And you may be familiar with design optimization, and if you are, you know that you have to search the whole space. If you're trying to find a top of a hill, so you can get as best of a view of the landscape. If you could think of the back in the 1800s when they were settling the West, you could think about being an explorer and you want to see the landscape. Right? Well, there may be many hills you can climb, but if there's bigger hills around you, you're not going to be able to see as much of the landscape as possible. So if you're looking for the top of the mountain, you want to look globally, not just find the first hill and climb up it. There may be many higher mountains around it. So you got to search that whole landscape, that whole space, to find the optimum. So why do we shoot for good concept generations? There's a lot of reasons. You may have heard of DFX, right? Design for X. Design for safety, design for reliability, design for manufacturability. Well, we can think of DFC. That's design for confidence. How can you have confidence that you've come up with a very good design if you haven't searched the whole space? You can think about searching the whole concept space as providing some level of robustness. If a new specification comes up early that maybe you didn't think of, or just came out of the evaluation process, unexpected things may happen. And the only way to combat that is to have a pool of concepts available that allow you to be robust to changes, to allow you to have confidence. We can talk about design for no surprises. You don't want to come up with a superior concept late in the game. You may already be prototyping one type of energy storage system. Maybe you think a fuel cell is an answer, and who knows, maybe a simple battery is the real solution. You don't want to be stumbling upon superior concepts late in the game when you've already, especially if you think about complex designs like a car. If you got to retool late in the game, your competitors may reach the market before you do. So you do not want surprises. You don't want a competitor to come up with a design that might be dramatically better than the one that you've come up with. That's another type of surprise. We did a nice ME450 project back in the early 2000s where we were looking at surgical helmet systems. And the idea was to keep blood off of surgeons, particularly in the head region. And we looked at a lot of benchmarks, and what we were finding is they all seemed to be going down the same path. And by sort of thinking in very creative terms, what we were able to do is to really define a whole new space of types of solutions that dramatically changed the game and actually made a lot of money for the sponsor. Furthermore, we need to be thinking not only about avoiding surprises, but about designing for the next generation. If you're going down a single path, that path is likely to begin from where you are, from an existing product, and doing things the way they always were is not a good way to achieve a next generation breakthrough. So we're looking for radical improvements here, so we need good concept generation. And we can look at this from the inverse way. If we talk about good concept generation, we can also talk about dysfunctional concept generation. And here are some red flags. If you're only considering one or two alternatives, and these are being proposed by the people in your group that talk the most, that is unlikely to be a good solution. Having the involvement of just one or two people, resulting in a lack of team confidence and commitment and a lack of diversity of ideas, that's likely to fail in the end. Failure to understand profoundly not only your project, but the related benchmarks, or even some benchmarks that may seem to be unrelated. But when we break down your project into its sub-functions, there may be benchmarks for each of those sub-functions. If you haven't explored that well, then you're likely to fail. And not using this idea of taking the best of sub-functions and combining them, taking partial solutions. Maybe each of the solutions may be ridiculous, but there may be a kernel of an idea in each of those. Just like in the shopping cart example from IDEO, that you can combine into a real nice solution. Failure to consider entire categories of solutions. Energy storage might be one example. Maybe you can use compressed air, maybe you can use a battery, maybe you can use fuel cell. By not thinking of entire categories, you may be lopping off entire vast regions of that forest where where that pot of gold may be. So these are some of the common types of dysfunctions, and what we want to do now is talk about concept generation really in 4 steps. So this is the process of good concept generation. So the 4 steps begin, and we can show it in the following diagram. So note here that we're looking at problem definition a little bit differently than we described it in class. So as you can see at the top here, we're talking about problem definition as developing profound understanding. That would be in the context of engineering specifications in Design Review 1. Moving beyond that now, once you understand your problem, you can then decompose it. And we'll talk here about functional decomposition, which allows you then to identify and focus on critical subproblems. So this is a divide and conquer strategy. Once you have your subproblems, then you can benchmark the subproblems. Up until now, you've mostly thought about benchmarking in the context of products or systems that may be similar to yours, not subproblems that may be similar to yours. And you can use the same benchmarking approaches that you used before Design Review 1, talking to experts or the lead users of a product, looking in the patents and the engineering or popular literature, looking at what competitors may be doing. And then to brainstorm, come up with your own original ideas. And this is something certainly you can do alone. A lot of the best ideas happen, as you may be aware, when you're actually not intending to think about your project. So one thing that rigorous problem definition and rigorous benchmarking does, and good group brainstorming, and we'll talk about some group brainstorming techniques in just a few minutes. What that does is it gets your mind working on the problem, and it may be that the most brilliant idea happens on your own. It could be it just happened to be at a stoplight and you stop and suddenly something pops into your mind, or you wake up in the middle of the night with a very good idea. I can actually speak of a personal anecdote along these lines. I'd been working on a project trying to reduce the environmental impact of metalworking fluids for over 10 years, with focus on recycling systems, on coming up with chemical formulations. And it wasn't until I'd been working on that problem literally for 10 years when I happened to be at an unrelated conference giving an unrelated talk when I saw a presentation immediately after mine, and it spurred on an idea that became a patent. It turned out to be the solution that was better than anything I ever could have imagined, and now it looks like it's following a commercialization path, and I didn't happen to be thinking about it. Sometimes that's what it takes, a very profound knowledge to come up with a truly innovative solution. So you're combining your existing concepts and your new concepts, and what you want to do is to classify them. So where the sub-functions sort of line up, what you can do is classify certain categories of solutions, and then say, okay, well, this particular class of solutions has some promise and we want to explore it more. We may be able to lop off a whole set of solutions for cost reasons, for lead time reasons, what have you. But then you take the best in class of your sub-functions and combine them, and that leads you to a set of concepts which then are evaluated in the transition stage. So we call those integrated concepts, which are combinations of sub-problems. So once you've then gone into the transition stage, you've done some rough evaluation, then that leads to new concepts. It may spur you to look at new benchmarks and other categories of existing concepts. So let's walk through this process, beginning with an example. Okay, to sort of bring this home, I want you to imagine that your ME450 project this semester is to develop a new handheld nailer, and that's for the high-end consumer market, so they're willing to pay a little bit for this. Of course, a hammer would be pretty cheap. This is a sort of a machine that's an automatic hammer. You can think about it that way, or what we call here a handheld nailer. The goal of the team is to consider alternative product concepts, assuming only that the tool would employ conventional nails as the basic fastening technology. So if you think that your energy source could be nuclear power here at the moment, that's okay. We'll later talk about concept down selection evaluation, where you want to get rid of the infeasible concepts, and you can imagine that a nuclear powered handheld nailer is maybe a little too high-end and a little too unfeasible. But the only constraint we're putting on this problem right now is it has to use conventional nails. Okay, so let's now envision what this problem definition stage looks like. We need to understand our problem, and then we will decompose it. So what understanding? Well, we can begin with what we can call customer requirements. We've also called these product attributes or product characteristics. This is the high-level qualitative characteristics that our handheld nailer is going to embody. So we're going to say here it needs to use nails. It needs to be compatible with nail magazines on existing tools. You don't want to force your end users to buy custom designed magazines. Even though you might be able to make more money for it, it might just annoy your customers. So we want to be able to use existing nail magazines. These are cartridges that contain nails. It better have enough energy to nail into wood. It's handheld, so it can't be too heavy. Inserts nails in a rapid succession, and that's a qualitative metric. You know, when we develop these engineering specifications, in the next slide here we'll start to put numbers on these things, but at this stage we're talking about attributes, characteristics, basic requirements. It needs to be lightweight, as we mentioned already, and you don't want there to be a delay after you signal the tool or you trip the tool. You know, just imagine if you press the trigger and you expected the nail to come out and it didn't come out, so you look at the barrel of it to see what's going on, and the nail goes directly into your eye. You can't have nailing delays here, and that would be a key characteristic or requirement. So once we have now a basic understanding, we want to convert this into a better definition using engineering specifications, and you've been through this process in Design Review 1. So we can get a lot more specific now. We could say that the nail lengths are going to range from 50 millimeters to 75 millimeters. There's going to be a maximum nailing energy of 80 joules per nail, and we can back that out of calculations, say nailing into wood, forces up to 2,000 newtons. The rate, we want 1 nail per second as a maximum, so that's a pretty good succession rate. We want the average nailing rate to be 4 nails per minute. If this system needs to recharge, then having this specification is going to be particularly important. Also, the form that the nailer takes is important. The ability to insert nails between standard studs and joists. Think about constructing a house. That's roughly 368 millimeters. So we need to be able to put nails into that size of an opening. We say the mass has to be less than 4 kilograms, which is still kind of heavy, and a maximum trigger delay of a quarter second. So we have our engineering specifications, and looking back at our tree here, we've developed, we can say, this understanding, and this is where you're at with Design Review 1. Our next step is to decompose the problem. So we take our requirements, we develop our engineering specifications, we get through Design Review 1, and now we decompose. And there's a number of ways you can decompose your project. For instance, you can break it down by user actions. So, for instance, for a nailer, the first thing the user may do is to move the tool into a gross nailing position. What we mean by that, it's not quite the final nailing position, we want to get it close. The second action would be to position the tool precisely and then to trip the tool. Trigger it, give it the information that we want to nail it at that point. So this type of functional decomposition by user actions works for products that have simple functions. If you try to do this with a car that has complex functions that many of which are not directly interacting with the user, this type of approach maybe doesn't work so well. Another way is to decompose by customer needs. And this is good for problems for which form is the most important part, and maybe the working principles of the technology, that's maybe a little bit less important. So, for instance, we can say that we're going to decompose this by customer needs, which we're having the nailer to fit into tight places. We want it to be able to fire in rapid succession and has a large nail capacity. This may not be the best way to break down this particular nailing application. So you can break down the nailer into three categories of inputs. And this is often a good way to break it down. You can trace the flow of energy. The energy coming in and the energy coming out. You can trace the flow of material. You've got nails coming in and you've got a driven nail going out. And then you can track the flow of information, the signal coming in and the signal coming out. What might that look like based on operations? Well, energy-wise, we could say that we need to store energy. And there may be many ways to do that. Then we're going to convert that energy, whatever form it's in, into a physical translational energy that's going to be applied to the nail and lead to the driven nail. So that's the flow of energy along the top here. If we look at the flow of nails, we can say that, well, the nails are going to be stored, and then a single nail needs to be isolated from the group of nails. And that single nail then is going to have energy applied to it, and that's going to be our driven nail. Information, well, we begin by triggering the tool, and the device, the nailer, needs to sense that we've tripped the trigger. Then the tool is triggered, and that's when we know to isolate the nail and to apply translational energy to the nail, again leading to the driven nail. So you can imagine that now that we've broken down our project into its subfunctions, that it is possible to come up with a multitude of ways, for instance, to store energy, to store nails, to isolate nails, to provide that information to the tool. And you can come up very easily. If you come up with 2 and 2 and 2, well, suddenly you've got 2 to the 3 or 8 concepts right there. And you can come up with a lot more than 2 for each of these. And this is a fairly simple product. You could probably come up with 15 or 20 ways to store or accept external energy, and we'll look at that as we move forward here. Also, I would like to look at a different example than the nailer, and let's just quickly take a look at a coffee maker. Many seniors in mechanical engineering, just to get their curriculum, develop something of a coffee habit, and if you make your own coffee, you might have thought about how your coffee maker works. So let's look at how a functional decomposition of a coffee maker might look, and we can look at the material, the arrows in yellow, and the energy, the arrows in red. Well, it begins with water that's being measured to a certain amount. You may have experienced pouring too much water into your coffee maker, and when the coffee maker starts, it maybe overflows. A well-designed coffee maker is not going to do that, but maybe some of you have had this experience before. You measure, you store, then you heat up the water, and it's that process of heating the water that provides some evaporation and bubbles, and the water then moves mechanically through its own force through the coffee grounds, right? So the water after heating then is transported through a tube and mixed with the coffee grounds, and you've got a filter typically that separates the hot coffee from the waste grounds, and of course the filter itself becomes a waste. The coffee is then stored, and if it's a glass jug coffee maker like this with a hot plate at the bottom, typically after the coffee is made, then either you leave the hot plate on and the coffee eventually burns and tastes nasty, or you turn that burner off and the coffee gets cold. Either way, you're fighting against this energy loss here. Energy goes into heat, energy is lost, and the heater energy is also lost through conduction through the glass jug here. So this would be another functional decomposition of a coffee maker, and if you think about a glass jug coffee maker, if you just thought about it, you might think, well, this is an optimized product. But certainly there are, if you even just go to a store that sells appliances, or a place like Target, or Kmart or somewhere, you're going to see a lot of different types of coffee makers. And one way to come up with many different types is to just break down these functions and to think about different and better ways of doing this. Now, once you've broken it down, how do you come up with better ways of doing it? That's the second stage of concept generation. That's what we call brainstorming, where we say the great enemy of new ideas is old ideas. So let's talk for a few minutes about what we do after we've broken down our concept and we want to generate new concepts. We call that brainstorm. So what are some of the rules of a brainstorm? Think back to the IDEO video when they were working on concepts for the shopping cart. These are the characteristics that you would have seen there. First, no criticism. That's the first thing. The best way to kill a brainstorming session is for a know-it-all to just sort of be stepping on ideas. The characteristic of a good brainstorm is that it's a very loose environment, and maybe 90% of the things discussed are going to be absolutely ridiculous, but that 10%, or the sub-possibilities created from ridiculous ideas, can be brought together into truly genius concepts. So no criticism. Evaluation comes later. You want to have documentation too. Brainstorming without documentation is a dangerous game. The idea here, simply assign somebody to capture key phrases. You don't want the recorder, the person who's writing things down, to be slowing down the process. So it could be key phrases, keywords, simple sketches. Just make sure things are captured. Video can work for this also, but to the extent that video might make people uptight, then you may not want to use that particular approach. Same goes for audio, I suppose. Generating as many ideas as possible as quickly as possible. So forcing, you can even stand in this circle and just go around and force people within 10 seconds to come up with an idea. It doesn't have to be good, it doesn't have to be valid, it doesn't have to abide by conventions. In fact, you may want to have a session where you're just deliberately violating conventions and maybe having some fun with it, relaxing. Those are the rules of an effective brainstorm. So what are some of the tools? If you find that coming up with 200 different concepts is a challenge, what are some of the tools that you can apply? And one thing you can do is you get together in a group is just warm up, and maybe you're not even talking about your specific project. Maybe you're coming up with wild ideas unrelated to your project. So what are 101 things you can do with roadkill or something like this? Just something to break the ice that might force you to get out of maybe some of the pressure you might feel from trying to get an assignment done. You might think about an idea ball. If you've got a soccer ball, football, hopefully something that won't hurt anybody, you can just hang out in the room and throw the ball to the next person, and it's that person's job to, maybe even within a certain amount of time, come up with an idea, and then that person can pass the ball around. Empathy. This is looking at your problem in reverse. What if you were designing a nutcracker, so this would be a tool to crack open a nut. And what if you looked at it from the reverse direction, and you thought that, from the perspective of being a nut inside of a nut shell, how would you get out? And that's the idea of empathy, putting yourself in the position of your design intent. Wishful thinking, would you want to have a racquetball court in your airplane? Reality aside, what would be a great solution? The Airbus 380, through its design, leads to a number of potential pleasures that one typically wouldn't imagine in transcontinental flight. Analogy. This could be biological analogy. You can ask the question, how do birds do it? Or if you're designing a robot for locomotion, you might be inspired somehow by nature, maybe by a spider crawling. Or if you're trying to achieve some kind of a separation, you can think physical-chemically. How would a salt solution be separated using a membrane? Or for the case of our nail gun, what might a mechanical analogy be? Maybe a rail gun, for instance, could be an analogy. Thinking in terms of violating constraints, what would this project look like if there were no gravity? Simplification is a similar idea. If you remove part of the system and use that to look at new possibilities. What if you had a nailer that you didn't need to store energy on? What would that look like? And would that create then new possibilities? Systematic generations, brute force. Just look at all known solutions. Again, that means not just at the system level, but at the sub-problem level, at the sub-function level, and then doing this type of combination. We'll show you an example of that in just a minute. The final way is to just try to jump out. If you find yourself at a stall, you've hit a wall, then just try something ridiculous, and hopefully that restarts the process. Okay, so here would be an example of a brainstorm for the sub-problem, which is storing or accepting energy. So you see here using a high-pressure gas, or using a combustion process, gunpowder, using carbon dioxide that would be stored in a tank, using an electric wall outlet, hydraulics, a battery pack, a fuel cell, nuclear reactions, cold fusion, that's jumping out because that doesn't exist, using solar power or steam conversion, wind, or geothermal. This gets you thinking about ridiculous ideas, and you can see that now, if you've got 15 or 20 different ways to store energy, and then you've got 15 or 20 or even just 3 or 4 ways of applying translational energy to the nail, if we look at that subfunction, now if you look at each of these, you can talk about a single impact, you can talk about multiple impacts, at maybe tens or hundreds of impacts, or even hundreds or thousands of tiny little impacts leading to the nail being drawn in to the wood or pushed into the wood. Here's more of a constant push with a, maybe like a hydraulic cylinder or something like this you could achieve, and maybe twist and push. These are different ways, again, of applying translational energy to the nail. So if you look at, say, gunpowder, okay, can we apply gunpowder to single impact, multiple impacts, at the tens or hundreds level, or at the hundreds or thousands level, at the push, or at the twist and push? Here are 5 different solutions using gunpowder with different types of impact. We've got nuclear reactions with 5 different types of impact. So that's 10 solutions right there. And now if you've got 15 different types and 5, you can see that suddenly you've got 75 ideas right there, and it was very, very easy to do. And maybe 70 of them are ridiculous. But that's not the point. At the brainstorming phase, you've got a wide space where the pot of gold may be sitting in. And when we evaluate, then we can maybe prune down the solutions and look for the best ones. So a classification tree is a tool that does that. So if you look at where we're at now, we've defined the subproblems, we've looked at existing concepts and new concepts. These two words should be reversed here. Existing benchmarks and new concepts that come out of a brainstorm. We've got this wide space of potential solutions. And you've almost got the opposite problem. Before we had too few paths leading us to design utopia. Now we've got a bazillion different paths. So how do we figure out the right path? That's what this systematic exploration is, where we talk about a classification tree and then using a combination table. So a classification tree is essentially creating distinct classes where the solutions may either all be good or maybe are all nonsense. So for instance, we're going to lop off all solutions that involve nuclear energy just because we can't create it and we wouldn't know what to do with the waste anyway. This might look something like this for the nailer. We look at this function that is storing or accepting energy. That can be done chemically, pneumatically, hydraulically, electrically, nuclear, and we can just lop off the nuclear. And maybe hydraulic has some promise, but maybe we can't find the right type of hydraulic pump to fit into a small nailer cost effectively. So maybe we're going to lop off that branch. And maybe we're just going to run with the chemical or electrical just for the time being. And that's going to lead us to a number of different solutions that we're going to consider down the road. This is a way not only to organize your concepts. If you can get your concept generation organized in this type of a way, it's a great way to communicate with others. Maybe you're going to talk to an expert in hydraulics and they're going to say, you know what, there are low-cost hydraulic pumps that might be feasible for a nailer cost effectively. And you wouldn't have known that. Well, how do you even begin the discussion if you haven't classified your possible ways of storing energy? So this is not only an organization tool, it's a communication tool. And it basically demonstrates that you've searched your design space very, very well. And now somebody looking at your classification tree can then say, well, have you thought about cold fusion or some other type of way of storing or accepting energy? Have you thought about using a CO2 tank or some kind of stored gas? This facilitates discussion and possibly further brainstorming. Okay, so you have a classification tree from which then you can combine solutions. So you've got your different types of ways of storing energy. You can combine that, as we've already said, with ways of, for instance, applying translational energy. Each pathway, from converting electrical energy to translational energy to accumulating energy to applying that accumulated energy to the nail, each one of these is a solution. So if I'm going to use a solenoid to convert electrical energy, so we've actually pruned down here, and we're going to say now we're going to use electrical energy. And there's different ways to apply electrical energy and convert it to translational energy. We can use a rotary motor, a linear motor, a solenoid, a railgun. And each pathway through accumulating energy and applying translational energy to the nail, each one of these is a possible concept. So let's just do quickly the math. I've got 4 here, and I've got 2 here, so that's going to be 8 possibilities just looking between converting electrical energy to translational energy and accumulating that energy. And now we've got 8 ways then we're going to now apply the translational energy to the nail. So 8 times 3 that's going to be 24 solutions, just looking at a small part of that solution. So remember, what we're doing in the combination table is we're systematically now considering combinations of solution fragments to come up with something that may be feasible and may be novel and may be that utopic design that you were always looking for. Okay? So that's a way now we can go through this whole process. Again, being a bit repetitive here, but hopefully you're getting the point. That we're developing this understanding, we've got the specifications, and we decompose it. And we're identifying, focusing on the subproblems, and benchmarking and brainstorming at this level. That leads us to maybe 200 different solutions. We can classify them into groups. We can lop off groups that we're not very interested in, and then combine the best groups into integrated concepts. In the transition phase, then we do some rough evaluation, and that may take us right back up to the top, where we then start to benchmark and brainstorm new ideas. So we're going back and then going through this process multiple times. So hopefully now you've got a visual for concept generation in Design Review 2. You need to decompose your problem. You can do this any way you'd like. You can decompose it by function, by form, by operation, by key customer requirements. And we have a worksheet I'm going to talk about here in just a minute that can help you work through the functional decomposition process. Then you're going to document your brainstorming. And this is best to do in an appendix, so you don't want to encumber your well-written report by talking about all your brainstorming in the text. But you can certainly refer to figures in an appendix and then be very clear about the brainstorming process that you went through. And then create at least 5 different good ideas. You're hard-pressed to justify only having 2 good ideas. And you want to show that you've had tens, dozens of ideas and applying the idea of concept classification trees and combination tables. This is a way to demonstrate both your section instructor and your sponsors that you took this seriously. And even if you have a great design at the end of the day, it's hard to prove a negative, right? If you want to say this is the best design, how do you really do that without saying, well, we looked at all these other possible designs, and of those, this is the best? Right? So you have to go through this process of concept generation. We'll talk about concept evaluation in just a minute. But hopefully this is clear. If it isn't clear, you can contact your section instructor for more information. What I'd like to do next is to show you a functional decomposition worksheet that's available to you on C-Tools in the Resources folder under the folder called Course Worksheet. So go to the ME450 C-Tools workspace, click Resources, and then click Course Worksheets, and you'll see there a PDF on functional decomposition. Looking at our functional decomposition worksheet, what you see here at the top is that we need to begin by distinguishing function from form. As we talked about the nailer, we said we're basically looking at functions and functional decomposition. The minute you start talking about breaking down form, you've sort of locked onto a path already. So we call it functional decomposition for a reason. We're talking about breaking things down by function. Again, looking at the logical flow of energy, material, and information. Energy can be in many forms, and we could talk about flows, diverging flows, branching, converging flow. We could talk about information signals. Information can travel mechanically, optically, electrically. You want to think as broadly about energy, material, and information as possible. And the 2 main steps here that the worksheet walks you through is, first of all, defining the overall function that needs to be accomplished, whether that's a nail gun or whether that's a coffee maker. Be very clear about what this is doing, or else you're not able to decompose a system, because you don't have a system that really exists. Then you can decompose the function into subfunctions. You're documenting what happens, not how to do it. Using standard notation is something that's very important, especially if you're looking at schematics or software code. and you want things to be logical, in a logical sequence that helps you organize and understand and create new ideas. Matching inputs to outputs using a block diagram, for instance, can help you do that. And breaking down the functions into as fine a resolution as you possibly can. And there's really two ways you can do this. One is using an outline method, and the second is using a block diagram. And page 2 of the worksheet sort of works you through a case where you're using an outline. So here's where we're talking about a syringe, and the problem here is to provide a safe and inexpensive method to allow small amounts of sterile fluid to be injected subcutaneously into a sealed container, or maybe under the skin, right? Level 1 of the functional decomposition is the high-level requirements. It needs to remain sterile. You want to withdraw a fixed amount of fluid. You can't have air bubbles. You want to be able to adjust that total volume of fluid. You want it to be transportable to a person or to a container. That needs to be injected and disposed of safely. Maybe you want to use standard needles and fittings, for instance, lure fittings. This is level 1. Level 2 is moving in at a finer level of decomposition. So how can you maintain, what aspects of maintaining sterile conditions can you think of? Well, we've got to think about the needle and syringe, we've got to think about the packaging, and then the assembly. That all three functions involve maintaining sterility. We talk about withdrawing a fixed amount of fluid from a container. We can create sub-bullets there. Inserting the needle through the seal into the fluid, inverting the fluid container to submerge the open end of the needle and withdraw the fluid. We could do likewise for all the level 1. And next thing you know, you've got a whole bunch of sub-functions for which you can look for solutions and create a classification table and a combination table to come up with different types of syringes. Again, the focus is on function, not form, and we've already seen what this might look like at the block diagram level. Here's a case looking at a fingernail clipper or some tool to shorten excessive length fingernails. And the block diagram in the end may be complicated, looking again at material and energy and information as they flow through the sub-functions that may be established at the level 1 category. So hopefully with these examples you'll be able to now work your way through the functional decomposition. That's the key. Without a good functional decomposition, then there's not good concept generation. You don't have anything to classify, and you don't have any sub-functions to combine. And as we've seen already through these examples and through the IDEO example earlier in the semester, that breaking things down logically, there's really a process to coming up with good design. It's not magic. It's not a strike of lightning. It's something that comes through hard work. And we believe that between the tools of functional decomposition, classification, and then combination tables, you can generate a wide space, big forest to look through for that pot of gold that may be in there. Then the question is, how do we take this forest and then down select to that one pathway that takes us to the pot of gold? That is what we call concept selection, and let's take some time to talk about some very simple tools that you can apply to document your concept selection process. Having now talked about how we can create a boatload of concepts, let's talk about how we can refine and select. This is the transition stage that we're talking about, and it's quite an easy stage of the design process. This is not rigorous engineering analysis like we'll be looking at, particularly later in before Design Review 2 and before Design Review 3 when we're talking about optimizing the design. Here we're just assessing feasibility, we're comparing design concepts, figuring out what we should be developing further, and then trying to take the best of the best. And here we're still trying to move fast. We don't want to optimize every concept, because if we do that as a serial process, and we'll never get a completed project before the end of the term. So we're in this rough evaluation stage that we call the transition stage. Remember, we talked about why good concept generation is important. Let's talk about why good concept evaluation is important. Remember, we've got all these concepts now, and we want to arrive at an alpha design, and then that's our design review 2. And we may go through this process again, where, with feedback from design review 2, we're going to generate some more concepts, and then go through a vigorous concept screening and then concept scoring process. So there's 2 sub-elements of concept evaluation that we talk about. Concept screening, which might just be feasibility assessment, technology readiness assessment, or no-go analysis. And then we might take the most promising concepts and score them against each other. We'll do that before design review 2, and depending on the feedback you get, you're probably going to be generating more concepts and doing this again before design review 3. Where your time is shorter. And remember, design review 3 is your final design. That's an optimized design. So we're going to go beyond concept scoring. We're going to take that most promising concept coming out of this process. We're going to optimize it using engineering analysis. We'll be talking about that as the semester goes forward. Why do we focus on good concept evaluation? It should be obvious. We want products that are customer focused and competitive. We need to think about manufacturability, so the idea of design for manufacturability, product process coordination, time to prototyping. For instance, you want a design that you can actually prototype in the context of a semester. Especially if you're working in big groups, and 4-person teams are not that big. You may be involved in the future in much more complicated and complex designs where group buy-in and management buy-in might be very important. And documenting the decision process. Being meticulous here, because if something goes wrong or it comes up later, you need to be able to go back and retrace and even critically analyze your decision-making process. Without documenting that process, really there's no way forward. So that's really what we're doing here. And if we're going to take the concept selection process and draw it sort of diagrammatically, let's look at the techniques we would use. So we'll begin by saying, is the concept feasible? Use basic engineering calculations. Does the design break the laws of physics? Does the design require a technology that's not quite ready for prime time yet? And that really depends on the state of the art. If your technology is not going to be ready by the time you need your project, going back to the example of the nailer, if cold fusion would be great for you, but cold fusion's 50 years away, then clearly the technology is not ready. And that is sort of an absolute type of analysis. Either technology is ready or it isn't. The design is feasible or it isn't. We talk about absolute comparisons here. Similar for go, no-go. And we might ask some questions that are of a very practical nature, where we're saying, okay, we can go with this concept or we can't. For instance, we can list all the engineering specifications, and if all the specifications are a go, we meet them with each, with given design, we can meet each specification. Each specification is a go. Well, then you might just go forward with the whole design. Or for instance, if just a couple of specifications are not a go, you might then do some basic combination at this stage and make it a go. So then you can move into the next part of the evaluation process, which is to develop a selection matrix and then a scoring table. And these take your concepts, so you take all the concepts that can move forward, and then you score them relative to each other. Okay, so there are basically 5 steps you can use here. A feasibility judgment, a technology readiness assessment, a go, no-go screening, a selection matrix, and then a concept scoring table, which helps you justify which concept that you're going to develop. Remember, we're doing this against the customer.
requirements here, all the way up from the go, no-go screening down to the concept scoring. And we talk about relative comparisons for the selection matrix and for concept scoring. This doesn't make a whole lot of sense right now. Let's walk through each of these individually. Okay, beginning with feasibility judgment. Clearly, if it's not feasible, it will never work. So you can ask some simple questions. Why isn't it feasible? If something were different, could it be feasible? And is there some possibility you could make simple change that would allow the concept to be feasible? And you have to note the difference between feasibility and unpopularity. There's a tendency to do things in the future the way we've always done them in the past, and you have to be able to tell the difference between real infeasibility and maybe perceived infeasibility, just because maybe it could be your sponsor, people you're working with are just uncomfortable with the concept because it's different from things that have been done in the past. If it might work, if something else happens, well then you can assess the feasibility of something else happening. And if there is some feasibility there, you might want to keep considering it. So we can go from feasibility judgment to this idea of technology readiness. The technology needs to be mature. Typically, especially if you're working in large companies, they like to use things off the shelf. So they like to know things are manufacturable. They like to know that it's very well understood how the technology works. So just showing that it does work may not be enough. You need to understand how the technology works. Because if you don't know how the technology works, then there may be some variable in the field under which, and you might not have been able to predict that in advance, the technology or the approach might stop working. So we can talk about the operating environment. We can talk about failure modes being identified. And we'll be talking later in the semester in lecture about safety analysis and failure modes and effects analysis. So that's really an important part of technology readiness. Is there going to be some failure from a lack of understanding of how the technology really works, particularly in its operating environment? So here you want to be thinking, before you get to the design optimization phase, about whether there might be factors in the field that are unknown. And for that reason, you may want to shelve a particular design for a second generation, and given the time constraints, then develop a different concept, even if it does have some aspects that might be inferior, just because the technology isn't quite understood. So that's what's meant by technology readiness assessment. Once you got a feasible concept and you think the technology is ready, then do the go, no-go thing. List the engineering specifications and go back and just be sure that all the requirements are met. So do this twice. For each customer requirement, for each engineering specification, is it met or is it not met? If you have some of the engineering specs that are not met, you don't want to move forward with it, but it may be possible that you just make some basic modification or combine sub-functions from other concepts because you've got this great concept generation pool of ideas. You just pull something in and then you've got a concept that you can go with. And the idea here is not to have just one concept you go with. You're likely going to have 5 or 6 solutions that are possibly a go. So here's then when we move into concept selection. So let's just say that we've got 5 or 6 different concepts, A, B, C, D, E, F. Well, they're all a go. So let's figure out, if it's going to be, concept B that we go with, or D that we go with. Of the pool of goes, let's develop a selection matrix. And this is a very easy thing to do. What you do is you just list your concepts, and then you're going to rate them. And an easy way to do this is to rate the concepts relative to a baseline. So if there's some known way of doing this, or if you just want to use one of your concepts as a baseline, then you can just use pluses and minuses in each engineering specification or customer requirement. Say, is it better or worse? And then you just add up the pluses and minuses, and then you can rank the concepts on the basis of the sum. So here's an example, if I show you here, of a dosing example. This might be going back to the syringe, right? You've got a master cylinder, rubber brake, a ratchet, different examples. Here, just looking at the customer requirements. Again, you might want to do this with the specifications and the requirements. Here we're just showing it with the requirements. Using the master cylinder as a baseline, we can compare the rubber brake. Well, in this case, the ease of handling is the same. It's a 0. But the ease of use is worse. But the portability, well, they're about the same. Okay. So, actually, I messed that up. I called the master cylinder the reference when here, actually, the plunge stop is the reference. So, let me correct that. And we begin with our reference, which is D. It's all zeros. If we look at the master cylinder is better than the plunge stop in the area of ease of manufacture and portability. Whereas the rubber brake is worse than the plunge stop in the category of ease of use and ease of manufacture, but it's more portable than the plunge stop. You get the idea, right? Seeing is believing here, so what we do relative to the plunge stop, if we look at the number of pluses and the number of minuses, and we subtract the minuses from the pluses, so 2 minus 0 is 2. That's the net score. Clearly the reference is going to have a net score of 0. It's going to be all zeros here, 7 zeros for 7 requirements. And it turns out if we look at the net score for each of the 7 concepts here, you see that the highest number is 2. So that's something we want to move forward with. And a 1 is pretty good here. So that's something we probably want to move forward with. The reference is looking pretty good here. So we might want to take some of its attributes along with the lever set. And maybe we can combine it with each other or with some of the concepts we're going to move forward with, or even with some of the negative concepts. Right? If we look at the the dial screw, for instance, we see really it's just got one weakness here. Well, maybe we can take an idea from the plunge stop and now apply it to the dial screw, and maybe that will be something that's feasible. You can think about this as a combination table again, because that's exactly what we're doing. We're looking at sub-criteria now. We're looking at how the functions are achieved by looking at our functional decomposition, and we're revising, combining, and trying to come up with better solutions. There may be some that just have no good features whatsoever, and we don't want to consider them further. Okay, so this is a concept selection matrix, and it tells us, from the set of things we want to go with. There are 7 concepts here that we're moving forward with. We've gotten it down to basically 2 or 3 that now we're going to move forward with, or maybe 4 if we're going to actually combine them, right? So if we want to come down to an alpha design that is simply one concept, we can use a scoring table for that. And this is, again, a very easy process. What you want to do is prepare the selection matrix. So what that means is you want to add more selection criteria. Again, this is probably coming from requirements in the QFD, and you can even use the weights from there. And then you can rate the concepts numerically. Again, using a baseline kind of approach. If you define a baseline, then you can look at what's worse, what's much worse, what's better, what's much better. And then the idea here is to use the rating and multiply the weight by the rating. So that's something we didn't do in the concept selection matrix. We treated each requirement as if they were the same. A plus is a plus, and all pluses are the same. Here, we're multiplying the rating by the weight to get a clearer picture and a more resolved view of which concept might actually be the best. Right? And again, we have the opportunity to combine and improve concepts. So looking at the dosing example, here we are using the master cylinder as a reference. It has ratings of 3 straight down the dial, because that is the that is our datum, our reference. But here we look at the requirements and we've got the weights, and this presumably would have come before Design Review 1, right, from the voice of the customer in principle. So ease of handling has a weight of 5%, ease of use is 15%, and these are our selection criteria, and they add up to 100%. You can see I can multiply 5% by a rating of 3, I get 0.15. Ease of use times 3. 15% times 3, 0.45. I add up, down, I get a score of 3.00. I can do that for the concepts that I can combine, the lever stop, the dial screw. You can see we took some characteristics of the previous concept D combined with previous concept F. I took concept G and I enhanced it, called it a G+, and I followed this process. Okay. And one thing, engineers, they do like to get carried away, and sometimes have difficulty seeing the forest for the tree. Look at ranks 2, 3, and 4. You have 3.00, 3.10, 3.05. You have to imagine when you look back at these weights that those weights, they're not arbitrary, but they're probably not mathematically defined, and there's a lot of uncertainty there. And in fact, different users may have different weights. And so there's a lot of uncertainty here. So especially if these numbers are close in the total score, you got to take a closer look. So the 3.45 here being head and shoulders above 3.00, 3.10, 3.05, and that's clearly one that we're going to develop in this case. Again, you need to do some type of sensitivity analysis to make sure that this combined concept DF is really robust to expected differences in the weights. Too often, again, we treat these weights that we created in the QFD as gospel, and we don't go back and challenge them or even go back to our users once we have a concept like this with our alpha design, to ask the question whether it's sort of meeting the basic selection criteria. In fact, in Design Review 2, that's why we're forcing you to an alpha design, because oftentimes these criteria are not what we thought they were originally, probably aren't correct. So we need to have this alpha design that's expressed in Design Review 2 for your sponsors, for your section instructors, really to take a closer look and see if this is what we wanted originally. But even if it isn't, we found that we've got other concepts that we've generated, we've documented all this, so that if there are either new selection criteria or drastically different weights that we didn't think of before. For instance, look here. In selection criteria, you don't even see cost. Well, cost is important, right? So we've got the lever stop. We've made a commitment to develop this. You write up your alpha design, your Design Review 2, and your sponsor says, hey, what about the cost here? Cost doesn't, this ain't going to work. Sorry, we forgot that. So now we modify this, and we go through the process. Hopefully we've done robust enough concept generation that we've got lower cost options there. In our selection process, we can emphasize the cost question and include that here in our selection criteria, and now get to a point where we've got a more realistic scoring table. But you notice that it documents the process, what you thought originally and what you thought after some iteration. And iteration is very, very important. Hopefully you're beginning to understand the importance of a systematic process of concept generation and concept selection. If you ignore all this and you just keep moving forward and you're sort of laser beam focused on your first idea, you can imagine how many different ways that can go awry. Again, we've got that pot of gold in the forest, and if you just pick the first trail, you're unlikely to hit it. The more iteration, the more interaction, the more documentation, the better off your design is going to be, the more likely it is to, in the short period we have in a class like ME450, to achieve success. So just in summary now, this last part, after we've generated the concepts, how do we select? We go through the feasibility. judgment. We use our experience, we use engineering calculations, we look at the basic technologies embodied in our design against the state of the art, we ask the question whether it's ready, and we figure out which ones we're going to go with. These are yeses and nos, and goes and no-goes. We call that an absolute comparison. If the concept isn't ready, if the concept isn't feasible, if the concept doesn't meet some of our requirements and specifications, it's a no-go. With the set of goes, now we do first a selection matrix with the pluses and minuses. That's an easier process, and again, we're not trying to get to one concept, we're just trying to figure out which ones we should be moving forward with of the goes that are feasible. And we're looking for concepts that may just have a few deficiencies that can be pulled together, that when we ultimately score them, then maybe we figure out that one of that combined ideas turns out to be the one we want to develop. We get feedback on that, and then we go through the process again. That's what Design Review 2 is all about. I thank you for taking the time to watch this podcast. I hope even more that you're going to apply this over the next few weeks and have a most successful Design Review 2. Thank you very much.